So if we're going to find all the rational zeros for this given equation, we need to start by looking at what our possible rational zeros could be. To do that, we're going to take all of the factors of the constant, which in this case is 6. All those factors would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. We're going to take all those factors and we're going to divide by all the factors of what we call the lead coefficient. In this case, that's 10. So factors of 10 would be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. If we divide all that out, well, let's see, for starters, I would take all the values I have up here, divide by plus or minus 1. That would give me all the values from the top back. Next, I'll take all of these values here, divide by the plus or minus 2. If I take 1, divide by 2, I get plus or minus 1/2. If I take 2, divide by 2, I get 1. If I take 3 divided by 2, I get plus or minus 3/2. And if I take 6 divided by 2, I get 3 back. Okay, now I'm going to take all the numbers up here, divide by 5. Taking all those values, dividing by 5, I get plus or minus 1/5, plus or minus 2/5, plus or minus 3/5, and plus or minus 6/5. And finally, we'll take all the values from up here and divide by 10. We'll have plus or minus 1/10, plus or minus 2/10, which is 1/5, and we've already listed that, plus or minus 3/10 rather, and then we'll have plus or minus 6/10, which we already have up here because that's listed as 3/5 if we reduce. So we have all of our possible rational zeros now listed. As far as finding the actual rational zeros that work for this equation, we've now narrowed this down to a pool of numbers we can play with. Or if we select any of these numbers and we place them in our little box here for synthetic division, say I start with 1, I'll spell out all the coefficients on my function up here that equals 0. So those coefficients would be 10, 9, negative 19, and 6. What I'm trying to do now, using synthetic division, is I'm trying to see, for the numbers I'm choosing and plugging in the box, if I can get a remainder back over here of 0. If I do, then I know that I've got a rational zero here that works. So trying out 1, bring down 10. 10 multiplied to 1 is 10. Add through, get 19. 19 times 1 is 19. Add through, get 0. 0 times 1 is 0. We find that 1 is not going to be a rational zero because I did not get a value of 0 back here in my remainder box. So we're going to have to pick a different value. And obviously with all the choices we have here, it can take a little while. So to speed up the process, if we choose negative 2, in this instance, we should find that negative 2 works. So now that I know negative 2 works, I know one of my rational zeros, which is a solution here to this equation. So I could say x is going to equal negative 2. Now the question becomes, how many rational zeros are there to find? Well, potentially there are 3 to find. I know I have a degree 3 polynomial here set equal to 0, so potentially I'm going to have 3 rational zeros, or 3 solutions here to this equation that could be rational. Where I'm at this point in the problem, I know that I've gone down at least 1 degree because the 10 here represents the coefficient on x squared. The minus 11 represents the coefficient on x, and then 3 is my constant term. If I take this resulting quadratic, set this equal to 0, now solving for x, perhaps I can factor this out to do so. Let's see how this breaks up. On the last positions, we know we're going to have a 1 and a 3. We know the signs on the 1 and the 3 will have to be the same. As far as 10x squared is concerned, if I want to put something in the lead positions that multiply to give me that, Looks like I could try 2x here and 5x here, because if I make both of these negative and check my outside and inside terms, that should get me back to that negative 11x I need. So I've got two factors here that equal 0, meaning 2x minus 1 would equal 0, or 5x minus 3 could equal 0. If I solve for each of these respectively, over here I'd add 1 and divide by 2, x would be 1/2. Over here I would add 3 divided by 5, and x would be 3/5. So all of my rational zeros for this particular equation would include -2, 1/2, and 3/5. All right, so we got another example here to try. This one's a little less specific in terms of the types of zeros we're asked to find. It just says find all zeros. It doesn't necessarily say find the rational ones. We found on the last example that all of our answers happen to be rational solutions. But here, just finding all of the zeros in general, we'll start the same way. We'll mind our p's and our q's. This gives us some possibilities to test out. And again, to test out these possibilities, we start by taking all the factors of the constants. So in this case, we're playing with a -4. Values that multiply to give me a -4 would include plus or minus 1, plus or minus 2, and plus or minus 4. I'm going to divide that by all the factors of my lead coefficient. So here my lead coefficient is 3. Factors of 3 would be 1 and 3. As I work through the division here, I'm taking this entire top row here, I'm dividing by 1. That gives me that top row back. Now I'm going to take this entire top row, divide by 3. So I've got plus or minus 1 divided by plus or minus 3. That's plus or minus 1/3. Got plus or minus 2 divided by plus or minus 3. That's plus or minus 2/3. And you got plus or minus 4 divided by plus or minus 3. That's plus or minus 4/3. So these are all possible zeros that we could consider as potential solutions here to this equation. Now from this little pool of values, I'm going to select numbers, and I could do this at random, to plug into my box for synthetic division. As I plug into the box for synthetic division, so say I start at 1 again like I did on the last problem, the coefficients I need to spell out next to this box come from the polynomial in the equation. So that's 3x cubed minus 10x squared plus 10x minus 4. There are my coefficients, making sure every term is accounted for. My goal is to find a 0 here where if I plug it in the box, I get a 0 back over here for the remainder. So let's see if 1 works. Trying out 1, I bring down 3. 3 times 1 is 3. Add through here, get -7. -7 times 1, -7. Add through here, get 3. 3 times 1 is 3. Add through, get -1, so I don't get 0 back. We find that 1 is not going to be a 0 here for this equation. So fast forwarding, I think we'll find that if we try 2 and we put 2 in the box, that should work. All right, so we've tested for 2. We now see that 2 works. As far as our zeros are concerned for this equation, because we have a degree 3 polynomial, we're going to have up to 3 solutions here. So one of those solutions, one of those zeros, is going to be x equals 2. We've still got to find the other 2, though, that make up the remaining solutions or zeros to this equation. So at this point in the process, the coefficients that I have down here, we go down a degree from where we started. So we started degree 3. Coefficient for 3 is going to go with an x squared. Coefficient of -4 goes with the x. And then 2 is my constant value. If I take this and I set it equal to 0, now because I have a quadratic, I could try factoring this out to solve. We actually find through factoring on this one, this is not factorable. So the other route we have to go, we can use the quadratic formula. So using the quadratic formula, knowing a is 3, b is -4, c is 2, I start with -b, so that'd be +4, plus or minus the square root of b squared, that'd be -4 squared, or 16, minus 4, times a, which is 3, times c, which is 2. That's all over 2 times a is 3, so 2 times 3 would be 6. All right, let's work on cleaning up this discriminant value a little bit. We find that x equals now 4 plus or minus the square root of our discriminant, which works out to be, we've got to take negative 4 times 3 times 2 first. So if we do that, we get negative 24. Basically, we're subtracting 24 from 16. If we subtract 24 from 16, we get negative 8. So our discriminant is a negative 8. That's all over 6. Now I got to work on breaking down that root I have there, that square root of negative 8. Because I got the negative, we know we're going to take that negative out by placing an I outside the root. The square root of 8, we also know we can simplify a little bit further. The square root of 8 is simply 2 root 2. So breaking this down, I find x equals 4 plus or minus, it'd be 2I root 2 all over 6. At this point, I check to see if I've got any common factors shared between my denominator and this 4 and this 2 up here. Common factor obviously would be 2, so if I divide 2 into all of those, 2 goes into 4 2 times, plus or minus, 2 goes into itself once, so it'd be I root 2, and that's all going to be over. 2 goes into 6 3 times. So I find here that I've got one rational 0 of x equals 2, so there's one rational solution to the original equation that's given. And then I find that I've got 2 complex roots or zeros or solutions for this equation. And I know I have 2 here because of the plus or minus. So because we started with a degree 3 polynomial that was set equal to 0, I now know I've got my 3 solutions I need. All right, so now that we hopefully have a fuller understanding of how we can arrive at these roots or zeros as solutions to these equations, let's try to go the other direction. Let's see if we can come up with a polynomial equation which would have some roots already given to us. If we know we've got roots of negative 1, 2, and 4, then we know those roots lead us to factors. In other words, if negative 1 is a root, I know that x minus that negative 1 or x plus 1 must be a factor of the original polynomial. If I know 2 is a root, well, x minus 2 must be a factor, and if 4 is a root, x minus 4 must be a factor. Now we're asked to find a polynomial equation that has these roots. Since it's an equation, we're going to let this equal 0. We know if we solve this right now, we'll go right back to these roots or these solutions to this equation. So to find the polynomial, since we're going backwards, we need to multiply all this out. Really, you can start with any of these binomial combinations, but I'm going to start with these last 2 right here. And I'm going to understand that x plus 1 is coming along for the ride at this moment. If I start with these last 2 and FOIL this out, well, x times x would give me x squared. The outer term here would be a negative 4x. The inner term would be a negative 2x. If I put that together, that'd be a negative 6x. And if I multiply my last, negative 2 and negative 4, I'd get positive 8. Now I'm going to take that x plus 1, that binomial expression, multiply it through to the x squared minus 6x plus 8. To do that, I'm going to start with this x right here and distribute that through. As I distribute that x through, I get x cubed minus 6x squared plus 8x. And now I'm going to take the second term in this binomial expression, that 1, and I'm going to distribute that through. As I multiply through that 1, I get plus 1x squared. I get minus 6x, and I get plus 8. All of this equals 0. So now really the only thing left to do is combine like terms. If I combine like terms, I have x cubed be minus 5x squared, because I have a minus 6x squared and an x squared. It'd be plus 2x, because I have a plus 8x and a minus 6x. plus my constant of 8, all of that equals 0. So there's a polynomial equation where I know if I solve this equation, the solutions I would get back would be these roots up here, -1, 2, and 4. All right, so let's do another example here where we have to find a polynomial equation, only this time some of the roots that we have to play with are going to be complex. So what that does now to this process? Well, the process really remains the same. For instance, if I start with this -2, because that's probably the easiest one to understand at this point how to set up, we know the factor that would correspond to a root of -2 would be x plus 2. If I start by building off of that, now I'm turning my attention to the complex roots. If I start with this 3 plus I need to understand that the factor that would provide that root to me would be x minus whatever that root is. In this case, that root is 3 plus I. I'm going to subtract that 3 plus I then from x. And then similar idea with this complex root of 3 minus I set up a factor of x minus the x minus that complex number of 3 minus I. All of this will equal 0 since I'm trying to set up a polynomial equation. Now, as I start to multiply everything out here, again, I'm going to turn my attention to these last couple of quantities. And I'm going to notice inside these quantities that I am subtracting the entire complex value here of 3 plus I. So that means I need to change some signs. I'm going to have a minus 3 here. I'm going to have a minus I here when I distribute that negative through. Likewise, in this second factor here, this last factor, if I take this negative and distribute through, I got to change my sign, so that's a -3 and that's a plus I. All right, multiplying all this out. As I multiply this out, I'm understanding that the x plus 2 is a factor that just is kind of remaining in the front until I'm ready to play with it. But if I multiply everything out I have right here, I'm going to start with this x, and I'm going to distribute this x through. If I distribute that x through, I've got x times x, which is x squared. I've got x times -3, which is -3x. I've got x times that plus I, so it's plus I x. Now, I'm going to take the -3, which is right here. I'm going to distribute that through. As I distribute the -3 through, I've got -3 times x, which is -3x. I've got -3 times -3, which is +9. I've got -3 times positive I, which is -3i. And finally, we get to this negative I right here that I'm going to take and distribute through. When I distribute this negative I through to x, I get -ix. When I take negative I times -3, I get +3i. And when I take negative I times positive I get negative I squared. Now all of this equals 0 in the end. At this point, I'm looking to clean up what I have right here. So in the next step, I carry my factor of x plus 2 down. It's still waiting its turn. But cleaning up this big mess I have from the previous step, well, I should find, as far as the x squareds are concerned, we just have 1x squared. I should find if I start joining x's together, I've got a -3x and a -3x. It appears to be the only x's I really have to play with, so that's -6x. Because the other x's that are present here have i's in them. In fact, those cancel each other out. Working my way through the rest of this, I notice there's a -3i and a +3i, which cancel themselves out, leaving me with a constant value of 9 that I have not yet considered, and this -I squared. Well, with what I remember about I squared, I remember I squared is equal to -1. So I'd be subtracting -1 here, meaning I'd be adding 1 on. So if I take my constant of 9 and 1 here, put those together, plus 10 results. So I know I'm doing these correctly if I'm starting with complex roots. that are helping me to form these factors, and when I multiply out that entire portion that involves all those complex roots, all the i's go away. That's how I know I'm doing this correctly. So finally, I'm ready to take that x plus 2, multiply that through to this x squared minus 6x plus 10. If I take x, distribute that through first, well, I have x cubed minus 6x squared plus 10x. And if I take that plus 2, distribute that through, we've got plus 2x squared minus 12x plus 20. All of that equals 0. Combine like terms, and we've got our polynomial equation. So we start with x cubed. Got a couple x squareds I can put together, which give me minus 4x squared. A couple x's I can put together, give me minus 2x. Got my constant of 20. All of that equals 0. There's my polynomial equation, which would give me roots of 3 plus I, 3 minus I, and negative 2.